Welcome to Mr. Strauss's Chemistry Corner. This is the specific heat lab edition, the one you've been waiting for. And to all my Polish viewers out there, jak się masz. So, I have followers. I do. I've got some in Alaska, some in Canada. There must be pretty boring and never mind, I'm never going to say anything bad about anybody's country, especially on, the internet. So we love every country in the whole United States. So, number one, we are going to calculate the specific heat of your unknown metal. I'm going to go very slow. So I'm going to draw a picture, and it's the picture of your calorimeter. There is water in the calorimeter. And we put in how many grams of water?
100.
100 grams. So the mass of your water should be 100 grams. The initial temperature of the water, what was the initial temperature of your water, Jayla?
98.3.
That was the metal, okay? We put metal in boiling water.
Oh, dang.
That's all right. You won't be the only one, but what was it? What was that number you said?
For the metal?
Yeah.
98.3.
98.3. So we got the metal up to boiling by putting it in boiling water, but the water inside your calorimeter was
23.4.
23.4. How much was the mass of the metal, Jayla?
Oh. 63.467.
63.467. Okay. Grams. So we had that mass of metal. We put it into boiling water. That's why it's so hot. We dropped it into 100 grams of water in our calorimeter. So I got. And if we put a hot metal into cold water, what's going to happen to the temperature of the water?
Go down.
Get hotter.
It's going to get hotter, right? Because you just put a hot metal in cold water.
Oh, I thought the metal was cold and the water was boiling.
Nope, other way around.
Sweet.
So that means the final temperature is going to go up. And what was the final temperature of your water, Jayla?
27.4.
27.4. Okay. The specific heat of water you look up in the book. And the specific heat of water is 4.184 joules per gram degrees Celsius. Yeah.
For the TF of the metal, is that supposed to be at like the 98.3?
Oops, nope, that should be T initial.
Yeah.
That's the initial temperature of the metal. So once again, the mass of the water is 100 grams because we measured out 100 mils. We have our initial temperature of the water, the final temperature of the water, and the specific heat of the water. The mass of the metal you got on the balance, the initial temperature was near boiling, and the final temperature of the metal should be the same final temperature as the water. What we don't know is the specific heat of the metal. That's what we're trying to find in this lab, is what the specific heat of the metal is. Now, where did the heat from the metal go? Where did the heat from the metal go? Into the water. Now, the amount of heat lost by the metal is equal to the heat gained by the water. Okay? Right? Remember when I did that analogy where I took out $3 and I gave it to Riley? If I'm minus $3, Riley is plus 3. So if
It landed on the whiteboard.
if I am minus heat, right? Because if you're losing, you're minus. If I'm minus $3,
What's the Q?
Q stands for heat, right? If I'm losing heat, who's gaining? The water, okay? And the amounts are equal and opposite. So again, if I lose $5, I'm negative $5. If Riley finds it, he's plus 5. So I'm minus 5, he's plus 5. They're equal but opposite, so we have the negative sign. What is the formula for Q? The formula for Q is this. The mass times the final temperature minus the initial temperature times the specific heat. That's the formula for Q. Now we're tackling the toughest problem first. The problems you're going to do for homework are going to be easier. So it's kind of, in one sense, nice that we're doing the toughest math problem first. Okay. If this is Q, if this is the formula for Q, and I'm dealing with the metal, then I'm going to expand this equation out like this. Negative mass of metal times the final temperature of the metal minus the initial temperature of the metal times the specific heat of the metal is equal to the mass of the water times the final temperature of the water minus the initial temperature of the water times the specific heat of water. Now that looks like a long equation. That's only because it is. You've got the mass of the metal times the temperature change, the final minus the initial of the metal, times the specific heat of the metal is equal to the mass of the water, the final temperature of the water minus the initial temperature of the water times the specific heat of water. Why the negative sign? Again, because the metal's losing, the water is gaining.
So it's the negative mass?
So negative, think of it more of as negative times all of this. Okay? Just like if I'm negative $5,
Yeah.
it doesn't mean the dollars disappeared, it just means I lost them. Someone else gained them. Does anybody need a calculator? Because you're going to need it quite soon. You do one? Calculadora?
Were these last two the same?
Now the reason why I write down all of the information is so that we plug it into the right place. So now we got to plug in our info. So the negative sign, don't lose that negative sign, it's still there. Negative 63.467 grams. Our final temperature is 27.4 degrees Celsius minus the initial. Do we know the specific heat of the metal? No. That's our unknown. That's what we're trying to find. The mass of the water is 100 grams. The final temperature of the water is 27.4 minus the initial times the specific heat of water.
Where'd you get the
Wait.
4.18?
The 4.184 we look up from the book, that's the specific heat of water. Yep. Graham.
So should your final temp of water and final temp of metal be the same?
Yes, because when any two things touch, they will eventually reach the same temperature. Now before you start solving it, let's just work through it together slowly. You have subtraction here. So you gotta do the subtraction first. So 27.4 minus 98.3. When you do subtraction, you care about where's the guess. So our guess is in the tenths, so we're going to round to the tenths. And so it's going to be a negative 70.9. So that means on the left side, we would have negative 63.467 grams times a negative 70.9 degrees Celsius times the specific heat of the metal. On this side, we do the subtraction as well. It's 27.4 minus 23.4. Here's my guess. Here's my guess. I round to the tenths. I end up with 4.0. So 100 grams times 4.0 times 4.184 joules per gram degrees Celsius. So now, what's a negative times a negative? Positive. So I end up with 44,099 times the specific heat of the metal is equal to 100 times 4 times 4.184 which is 1673.6. The last step then is to divide If I'm going to divide that side by 44.99, I have to divide this side by 44.99.
Don't you have to go to only 266?
And you're right. We're going to round our final answer to two significant figures because this number has 5, 3, 4, 2, and 4.
So you don't round it till the end?
So you don't round it till the very end, and you're going to round to two significant figures. So when I do my calculation, I get .3719, but I'm going to round it to two significant figures, so it rounds out to 0.37 joules per gram degrees Celsius. And that's the specific heat of the metal.
So what do you do when you're timing those two? Do you write the whole number down, or do you round?
Since you have your calculator,
Just write it like that.
you can just write it out like to the tens place or to the ones place.
Do you always write
Because
like
it's
that?
not going to matter.
Yeah, right.
It's not gonna matter
The way I hope.
because you would be rounding.
Yeah.
If you are stuck, let me know. Don't move on to the next problem because I want to make sure everybody's doing this right first.
What is this one? 35.9?
Yeah.
I don't know, that's not right.
Graham, what did
That was your time.
The same as those two.
Graham, what did you get?
8,
I think it should be different.
870.
Maybe it's supposed to be different.
I know this is kind of tough, but this is a great use of your algebra.
You didn't have the same stuff though. But you had the same temperatures. I don't know. Yeah, then you would divide by 4735.
It looks as if everybody's done it right. So, what I'd want you to do then is to redo this calculation, but now I want you to use your trial 2 data. So if you're going to use your trial 2 data, you just plug in the different numbers, okay? And then you'll average trial 1 and trial 2 together. And from those 2 trials, you will predict what your compound is. Because the sheet that I'm handing out gives you the specific heats. So aluminum, lead, tungsten, brass, gold, zinc, copper, tin, bronze. You can use your answer. So based on this data up here, 0.37 is pretty darn close to the specific heat of brass and copper. So go ahead and do trial 2 and average them together. 'Cause you might
Yeah, we're not close to anything.
The multiplication deals with the amount of.
Yes, the amount of.
So you only have one trial. So you're gonna loop, so now you can just skip to here and predict which one. So once you know your specific heat, you can calculate your percent error based on the actual value. So you take your experimental minus your actual value, divided by your actual value,
What was the, 4.1?
times 100%. So if you tell me your letter, I can tell you what the actual value is. Some of you already told you. And then in your summary, you put down your results, errors, and how to fix those errors. What was one assumption we made? Where did all the heat go?
Into the water.
Into the water. But did all of the heat go into the water?
No.
No. As you transferred it, some of the heat went into the air, right? When you dropped it into the water heated up, and then some of the heat from the water went into the calorimeter. So the temperature of the calorimeter went up. What else did you do during the lab? What does stirring do?
Heat it up.
Adds a little bit of heat. So those are all things that you could actually take into account by the calculations. If we wanted to, we could actually calculate the temperature change of the calorimeter and how much it went up.